Please turn off your microphones. Ahmed and Ali, please turn off your speakers from here. Okay, you can click on Control D to turn off your speakers. Now I start. Multiple people wants to join this call. I think uh, I admitted the others. Okay, so I start presentation. As you know, this webinar is about meshing, partitioning, and mesh design. And this is the table of content of this webinar. And actually, we must do a lot of works in 1 hour. I hope I can finish it in 1 hour. And that's it. Okay, before talking about mesh design, I want to talk about our 50% discount code, which is active until 12th of March. Also, we have a video for informing it in our YouTube channel. Here I will put its link when I put the video of this webinar in my YouTube channel. And if I show you my YouTube channel, this is that video. Okay, this is that video for discount code, and you can watch it. But actually 50% discount code is for people who do not participate in this webinar. For you who participate in the webinar, instead of 50%, this discount code is 70%. If you want to sorry, let me admit others. If you want to buy 1 or 2 premium tutorials, or a 1 or 2 extended premium package, and 1 or 2 chapters from the comprehensive Abaqus package, but the code applies to the entire comprehensive package with a 50% discount. And what is the comprehensive Abaqus package? This is our package, which is for beginning to advanced stage, and it includes 40 hours of recorded video. And also you can buy one of its sub packages according to your major. The mechanical sub-package includes 36 hours of instruction, and civil sub-package or structure sub-package includes also 36 hours of instruction. The steel structure sub-package includes 33 hours of instruction, and essential sub-package includes 20 hours of instruction. And also here I will put its preview when I upload it in my YouTube channel. And also if I show you in my YouTube channel, here it's its introduction video, and also each chapter of it has its own preview. You can see them until here. And the sub packages, each sub package includes some of the chapters. Okay, so their price is less than the complete package. And also if you want And I forgot to say something. The prices of all of our premium tutorials and extended premium packages and other and the comprehensive package is mentioned in the description, okay, in the description of each tutorial, but the prices are without considering discount. And you can use the 50% discount code to buy them, and you can text me. Yes, until 12th of March, 50% of the mentioned prices will be accounted for you. And also, if you want to buy the full package or its sub packages, but also for the others, I mean, if you want to buy 1 or 2 premium tutorial, 1 or 2 extended premium package, or 1 or 2 chapters from the comprehensive Abaqus package, the discount code for participants is 70%. And also you can pay this amount in 2, 3, or 4 installments according to your budget or income. Now I go to talk about the mesh design, and first I start with element specifications. Is it recording? Yes, it is recording. And an element has two main specifications. One of them is element shape and the other is element type. Element shape can be quad or tri or hex or tet or wedge. Okay, quad and tri are for 2D space, and hex, tet, and wedge are for 3D space. And element type, also for element type, we have element library, geometric order, and formulation. Um, in Abaqus, as you know, we have two structural solvers, Abaqus standard and Abaqus explicit. And each of them has their own elements library. And also geometric order can be first or second. Okay, we have first order and second order elements. And about the formulation, we have full integration, reduced integration, hybrid, incompatible mode, and other kinds of element formulations. Here I have mentioned about element shape, and as it is illustrated here, this is the hexahedral element or hexahedron, and this is tetrahedral element, which is or tetrahedron, and also here we have wedge, and these are their shapes. Now I want to talk about mesh design. And here I want to tell you my definition of mesh design. The procedure of generating the desired mesh pattern, which ensures the accuracy of the simulation with the minimum number of elements, is called mesh design. To conduct mesh design, you must master mesh module tools. And here I want to mention two important complementary points about mesh design. Point 1. Generating fine mesh in all regions is not generally recommended because it leads to inefficient simulation. Fine mesh must only be defined in stress concentration regions, contacting or under load regions. Second point, in some problems, we can choose between different meshing patterns, but in some cases, only one meshing pattern guarantees the accuracy of the simulation. An example of this situation is the calculation of J integral and stress intensity factors using the contour integral method, which requires using the focused spiderweb mesh pattern. Actually, we use focused spiderweb mesh pattern to analyze cracks, okay? And when we want to calculate J integral or stress intensity factors, and I have several videos in my YouTube channel about this topic, and when I uploaded it in my YouTube channel, here I will put the link of one of them. Okay, so here I'm gonna talk about mesh design tools. We have three main tools for mesh design when you want to implement your desired mesh pattern. Okay, the first one is seeding edges, and by seeding edges, you can increase or decrease the number of elements locally or using the bias method. Okay, and in this webinar, I will solve several kind of mesh patterns. I will create several kinds of mesh pattern using this tool. The other one is partitioning, and by using partitioning, we dictate the required element shape for each pattern. And it means that, for example, you import a complex geometry into mesh module, okay, and at the beginning its color is orange, okay. Then by using partitioning and using partitioning tools, we change its color to yellow or green, okay, or a combination of them, and then we can mesh it using hex elements, okay. And also we will do it in this webinar for a complex geometry. And also I will use partitioning tools a lot in other examples in this webinar. And finally, choosing the appropriate meshing technique for each partition. And this requires definition of appropriate number of partitions with appropriate patterns and specifications, okay. And also I will generate meshing patterns, several mesh patterns using this tool. And we need all of them, okay. We need all of them to generate our desired mesh pattern. This is the first example of this tutorial, and this is a plate. It includes 4 holes, and as you know, there are a lot of geometries including holes in the engineering applications, and this geometry will be meshed using 7 different sets of mesh module settings to introduce each setting application and investigate different meshing patterns and rules. And also this example will be solved in the 2D planar space, but all the mentioned instructions can be used for 3D cases. This is the first set of settings, and I go to Abaqus to create the plate and start meshing. So here I click on this file. In example 1, first I must create the plate. So I go back here and I name it plate case 1. It means first set of settings. And here I set it to 400. It is 2D planar, deformable shell, and this. So I define this sketch. I use isolated point to define the origin, and I fix it. This is not mandatory, but as I want, I always do this. I create 4 holes, and this is 100. This is also 100, and this is 10. This is 10. This is 10, and also this is 10. And I use construction lines here, and I put them here, and also I put this point and the other ones on the construction lines. Actually, when you create a circle in Abaqus, you have always this point, okay? And you must put this point in 0 degree or 90 or 180 or 270. If you don't do this, it will make problem for you when you want to mesh it. And also I create another construction line, and again, I forgot to this is 25, and also this is 25. And also you can do this when you want to put them on the line. And also this distance is 25, and again I set this distance equal to 0, and also this one is 25. Here you can see that all the lines are green, so it means that this sketch is fully constrained, okay? And there is no need to define more constraint, and it is well defined. So we have it, and I go to mesh module to mesh it, and okay. So I go back to mesh it. This is the no, sorry. This is the first set of settings. Here I have only used the global seeds tool, and in this case no partitions are created, and the seed edges or local seeds tool is not used, okay? This is the simplest case, okay? And I set the size equal to 5, okay? And also for the mesh controls, it must be quad and advancing front with mapped meshing, okay? With mapped meshing, that's it. So here I mesh it, and we have this mesh, as you can see, like this. And this is one of the simplest mesh patterns that can be generated and used for simple to moderate FE simulations, okay? Now I go to the second case, okay? In this case, instead of using advancing front, I use medial axis, okay? And no partitions are created, and the seed edges tool is not used again, okay? Also, this is simple. I go back to the part module, I create a copy from it, I name it case 2. And when you copy a part, all of these settings will be copied. So we have it here, and I delete the mesh. The the global seed is 5 again, as we have it here. But I change the mesh controls, and I use medial axis, okay? I use medial axis and mesh it again. So we have this pattern. And this is another simple mesh pattern that can also be generated and can be used for simple to moderate FE simulations. If you compare these two mesh patterns, here I create another viewport, and we have these two patterns, okay? You can see that they are completely different. This one is defined via advancing front, and this one is created via medial axis. And here you can see that I have not defined any partitions, but this kind of pattern is generated. Okay, it has some advantages and some disadvantages. Okay, both of these meshing algorithms are effective. Okay, but as you can see, they define completely different mesh patterns. Okay, and you must have expertise to understand that which one should be used. Okay, in each case. And in this webinar, I want to tell you more about this and give you more explanations. Okay, so this is the 2nd pattern. Also, this is simple. I go to the 3rd one. In the 3rd one, for the outer regions, I mean the perimeter. For the perimeter of the plate, I use 10, okay, via global seeds, and for the holes, I use local seeds tool or seed edges tool, and for these elements, for these holes, I use 5, okay, element size is 5. And in the mesh controls, I set it to advancing front without mapped mesh. Okay, without mapped mesh. So I go to part. I create a copy from it. It is plate case 3. I go to mesh. I delete the mesh. It must be set to 10. Okay, it must be set to 10. And I use seed edges tool. Okay. And I hold on shift key because I want to select multiple objects. I select all of them. Here I set it to by size. It means that I want to set the element size. I set it to 5 and bias is set to none. Okay, it means that I want to have uniform mesh on these edges. So you can see that local seeds are defined. Okay, you can see that their how can I say, their label or something like that is different from global seed. They are circles, they are white circles, but these ones are pink or purple triangles. Okay, they are local seeds. Okay, and also some of them are quad, okay, or quadrilateral. Okay, and these ones, when you see these ones, it means that there must be a, a node. Okay, because here we have that point in the sketch. Okay, that point in the sketch, and if here I use this setting, okay, all of them will be quad. Okay, it means that it cannot be changed. Okay, but most of the time we use this tool. We use this tool because it is easier for Abaqus to change the number of seeds when generating the mesh. Okay, in only some specific cases we use this setting. So I go back here, and also I set it to quad, advancing front, and unmapped mesh. Okay, unmapped mesh. And I mesh it again. Okay, here you can see that in some regions we have larger elements, and in some regions we have smaller elements. And by using the unmapped mesh method, we have non-uniform mesh zones in which the element size changes. Okay, you can see that here the size is changing. We call this mesh transition. Okay, mesh transition. And here all the plate is a kind of mesh transition zone. Okay, all the plate is a kind of mesh transition zone. And due to the lack of partitioning, the mesh transition has been implemented in an uncontrolled way, okay, which leads to regions with undesired element sizes. Here you can see that around the hole we have a stress concentration, but here we have large elements, and this is not appropriate, okay? We must use partitioning, and by defining partitions we can avoid this, okay? We can avoid this, and I will do this in the next examples, okay, in the next set of settings. So we have enough number of elements around the holes. In the next one, I use the same settings, but we use medial axis instead of advancing front, okay? We use medial axis. So I go back and create a copy of it, and I name it case 4. And here I delete the mesh again, and I set it to medial axis, and I deselect minimize the mesh transition, and I mesh it again, and we will have this pattern. And here you can see that due to the use of the medial axis algorithm, no mesh transition zone is created and the mesh is uniform. So we can conclude that if you want to define mesh transition zone, which is important when you want to have an efficient model, you must use advancing front algorithm instead of medial axis. And by defining partitions, the mesh transition zones can be separated from stress concentration regions. For stress concentration regions, the medial axis algorithm can be used. For other regions, the advancing front algorithm can be used with the unmapped setting. Here I want to talk about why do we define partitions. We define partitions to increase the meshability of the structure and define hex elements on complex geometries. I will talk about this in the later on, okay, in the next example for meshing and partitioning the pressure vessel. And to have more control over the element size of each region, and to use a specific meshing technique for each region. The number and configuration of partitions depend on the mesh pattern which you want to implement, okay? And this is the meaning of mesh design. You set everything according to the mesh pattern which you want to generate. In the next set of settings, I use partitions, okay? Here you can see that I'm using partitions. And these partitions only provide control over element size and maybe better formation of mesh transition zones. If you want to reach other targets of partitioning, the partitions must be changed and be more complex. And we will do this in the next set of settings. Here I create a copy. Five. I delete the mesh and I use this tool to create the partitions. I define these partitions. That's it. And here in these regions, I set the element size to 2.5 and the bias is set to none. Okay? And for the perimeter of the plate, the element size is 10. And also for inner partitions, I use single bias. Okay, I use single bias for some of them and double bias for the others. Okay, what is the meaning of single bias? As you can see here, we have arrows. Okay, and in the direction of arrows, the element size decrease. So in the direction of arrow, the mesh will be denser. Okay, and in the double ones, from the middle of the line or from the middle of edge to the other ends, the element size decrease. Okay, so we do this. Why? Because around the holes I want to have small elements. Why? Because these are stress concentration regions. Okay, and we must calculate the stress field accurately around the holes. So around the holes we must have dense mesh. So we use these kind of arrows. And for all the regions, we set the algorithm to advancing front and quad. So here I set it to quad, advancing front, and unmapped. Why? Because I want to have mesh transition. Okay, I want to have mesh transition. And for the perimeter, it must be 10. And for these regions, I'm holding the shift key. I set it to 2.5. Also, for easier selection, you can set it to wireframe. Okay, to wireframe. And I select these ones. And I use single bias from 10 to 2.5. Okay, because here in the perimeter the element size is 10 and here it is 2.5. Okay, so here you can see that the direction of some of them is wrong. So I click on flip bias, I click one time, and then I select the edges which their direction is not correct. As you can see now, all of them are correct. That's it. And I select these ones. And also here, it must be double. It's correct. Now I mesh it. We will have this kind of mesh. And here you can see that the element size is small around the holes and it is larger in the perimeter. Okay, and if I compare these two, here we have mesh transition, but it is uncontrolled. But here it is implemented in a controlled way. So this is much better. And also here you can see that they are similar. And I go to the next one. In this one, I change the partitioning. And I define these partitions, these circular partitions with these lines, okay, in the radial direction of each hole. And it enables us to have more control over the mesh pattern. So I go back, I create a copy. It's 6. And I delete the mesh. Then here I delete the partitions, okay? And then I use this tool again to create these circles. And the radius is 15. So I create these ones and I create the circles. It is equal radius. No, sorry. They have equal radius and it is 15. And also I define the radial partitions. Implementing complex partitions takes some time. Now we have them. And then in the tangential direction, I set the element size to 2.5 and the bias is none, and for the perimeter it is 10. So I set it to wireframe and I select them again. I'm holding the shift key. $2.5. It is 10 again. And also in the radial directions also it must be 2.5. So I select these. $2.5. And for the regions around the holes, I use advancing front with mapped mesh, and for the other region, I set it to advancing front without mapped mesh. Okay, so I select these. And for this one, we have this pattern. The generated mesh provides an accurate calculation of stress concentration. This mesh pattern is suitable for damage initiation and damage propagation analysis. And by combining the 5th and 6th meshing and partitioning patterns, we will have more control over the mesh pattern even in the mesh transition zones. Here, this is the mesh transition zone, okay? And if we also define these partitions and use single bias and double bias again, we will have more control over this region, okay? And you can do it yourself. And I go to the next pattern, and this is the final pattern, the 7th set of settings, and this is more complex than the previous one, and it enables us to have the most control over the mesh pattern, and the meshing technique is changed to structured. Here you can see that its color is green. Okay, it's because I have changed the meshing method or meshing technique to a structure, but here it is free. Okay, as you can see, its color is pink. Okay, it's free. But notice that the how we use the free method in the 2D space is different in the 3D space. Okay, in the 3D space, the free method only generates tet elements or tetrahedral elements, and I will do this in the next example. So I go back and create a copy. It's 7th case, and I delete this, and here I create this partition. It's done. And I change the meshing technique to structured. And here we have two sets of edges. Some of them are in red, some of them are in yellow. Okay? For the red ones, I define 4 elements on each of them. And for the yellow ones, I define 5 elements on each of them. Okay? And these ones are 2 partitions, this one and this one. Okay, this one and this one. So 5 elements here, 5 elements here, 5 elements here, 5 elements here, and here 4 elements here, 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 4 elements here. That's it. First I delete the previous ones, and I start with red. Four elements. By number, I set it to 4. That's it. And on the remaining, 5. Okay, that's it. Here you can see you can see that why I did such this. Okay, this is actually the classic example for teaching mesh design. Okay, and if you can see, they are opposite each other. Also, they are opposite each other. Okay, so we select edges which are opposite each other, okay, and define the same number of elements on them. So we will have such pattern. And the generated mesh provides the accurate calculation of stress concentration. This mesh pattern is suitable for damage initiation and damage propagation analysis. In this mesh pattern, no transition zone is created. The 6th and 7th mesh patterns are appropriate for the analysis of bolt or pin connections using the Abaqus standard solver. This is because of contact issues, okay, and uh, in the circumference of the pin or bolt and on the circumference of the hole, you must have the same number of elements, and they must all the nodes must be near each other one by one. Okay, so this pattern is very good, and also this pattern, this meshing pattern, for analyzing the bolts and pin connections. If you want to define bolt and pin, okay, if you define connector instead of them, there is no need to do this. I go to the next example. It's according to this paper, okay. Also, in the future, I will create a tutorial according to this paper, and if I show you the paper, it is related to the analysis of pressure vessel, and this is a thermomechanical analysis, and it includes fracture mechanic analysis, and they have used XFEM method to analyze the crack. But here we only mesh it, okay? We only mesh this geometry. Okay. Here we have it here. In the second example, I have created it before the webinar, and then I import it to the mesh module. And here you can see that its color is orange. Okay, it means that we cannot mesh it using hex elements. Okay, if I set it to hex and mesh it, we will have this error. The selected regions cannot be meshed automatically using the assigned element shapes. They must either be partitioned, assigned a text shape, or manually meshed using the create bottom-up mesh tool. Okay, so in the first try, I don't partition it, okay, because I want to use tet elements, okay? I want to use tet elements. And I set it to tet, free, and I deactivate mapped mesh, okay? Because I want to define mesh transition zone, okay? And every solid geometry can be meshed using tetrahedral elements. In the Abaqus documentation, it is suggested to use second order tetrahedrons, which are C3D10 or C3D10M, instead of first order ones, which is C3D4. The accuracy of first and second order hex elements is more than that of first and second order tet elements. So first you must try to use partitions and increase the meshability of the structure to define hex elements, okay? And here I will do this in the second try. So for the other regions, I set the approximate global size to 300, and for the circumference of the nozzle, I set it to 50, okay? So here it's 300, and I use this view. Yes, all of them are selected. For these, I set it to 50. And also, sorry, here by default it is quadratic and it is C3D10. If you activate this, it will be C3D10M. And I mesh it. You can see that here around the nozzle we have small elements, and then in the other regions which are far fields we have larger elements, and they are second order. And now I want to use partitioning tools, okay, to mesh it with hex elements. How much time we have? Okay, we only have 8 minutes, I think. And here I create a copy from it. I write hex. This is a copy. I go to the mesh module, I delete the mesh, and I delete the seed edge tool. And okay, now I want to partition it. First of all, I use this tool and I select 3 points. 1, 2, 3. This is the first one. Also, I change the element shape to hex. You can see that it remains orange, okay? So we must define more partitions. Sorry. I must define more partitions. 1, 2, 3. Sorry, 3. It is orange again. Then I use this tool, extend face. I extend this face and it is changed to green. Also, I use this tool again for here. It also provides better partitioning. But as I want to define transition zone, okay, I change it to sweep technique and advancing front and unmapped mesh, okay, for the shell section. But for the nozzle, it is a structure. So I select these regions. It is the shell part, sweep, advancing front. And the global size is 200. And for these regions, for these partitions, okay, I use single from 200 to 50, okay. Also for the thickness region, thickness partitions, I use 4 elements. So I select these edges using the shift key. I'm holding the shift key, single, 50, 200, and this one must be flipped. Very good. I select these lines or partitions in the thickness direction. I'm holding the shift key. This one also. I think I have selected all of them. I want to have 4 elements along the thickness. And also in the thickness of the nozzle, I want to have 4 again. And for the length of the nozzle, I want to have element size to be 50. So this one, by size, it must be 50. Okay. And it must be 4. And also for these regions, 50. The circumference of the nozzle. This is the circumference of the nozzle. It must be 50. That's it. Now I create the mesh. And here we have this mesh. And as you can see, here we have small elements around the nozzle. I don't know why the Google Meet didn't give me a warning because in the free plan we only have 1 hour. Okay, but it shows that I think we can proceed for more than 1 hour. It's very interesting, and it means that you are lucky. You are lucky that okay, so we had this mesh. We have this mesh. As you can see, it will provide us accurate stress calculation. Yes. Please ask Hossein. Please ask your question at the end, okay? Because I'm not sure that maybe Google give me the warning again, and so, but I think it will not. But I want to be conservative, okay? I want to be conservative. So I go ahead, and then at the end, I hope that we will have enough time for Q&A. This is the third example. It's according to this paper. I want to show you the paper. We have already a tutorial according to this paper. This is the tutorial for simulating the moving loads. And when I upload the video on my YouTube channel, here I will put the link to that tutorial. Also, it has an extended premium package. Here you can see the mesh transition zone. Okay, they have used TET elements. Okay, they have used TET elements to create mesh transition zone. And also this is our actually I only want to show you these ones. And here it is also another example of creating mesh transition zone using TET elements. Also here we have a crack, and here we have the focused spiderweb mesh pattern. And if I show you this, if I want to show you this geometry, it is one of the examples of the fifth chapter of my comprehensive Abaqus package. Here you can see that I have set these two regions to mapped, unmapped try. It is deactivated, it is TET. And also I want to show you the seeding pattern. For example, if I set it like this, no, it's better to show you in this way. For example, this one. You can see that in the direction of the arrow, actually, I set the direction in a way that it is the direction is to the stress concentration region. Okay. Also here. Here. And here. But for the other edges, for these edges, and this one. Oh, also this one I didn't select it. For these ones, if you see, I have set the bias to none, okay? Because these edges are far from the stress concentration, okay? They are far. And so here you can see that finally we have this kind of mesh pattern. And if I show you half of it, in the stress concentration region, here we have crack, okay? Crack is here. You can see that here we have small elements, but in the others we have large elements, okay? Because here we have far field, okay? And there is no need for the accurate stress calculation. And also another example is the impact, okay? High velocity impact. Also it can be used for low velocity impact. And the impact region, as here we have damage initiation and damage propagation, we use uniform mesh. We use uniform mesh, and it is the second example of 11th chapter of comprehensive Abaqus package. And if I show you it, is it? No, this is its video. Hex medial axis, okay? It provides uniform mesh for us, like this one. Like, sorry. If I show you here, like this, uniform. And here, it is advancing front unmapped, okay? Because we want to have mesh transition, okay? We want to have mesh transition. Because here, we don't have damage initiation and damage propagation. Only here we have damage initiation and damage propagation. So here we must have uniform mesh to have accurate simulation, but in the other regions, it is not needed. That's it. And for FEA consultancy, you can contact us via Telegram or WhatsApp, or you can send email to us. And here, these are our services for FEA consultancy. Okay. My presentation is finished, and here Google Meet didn't give me warning, so we can continue. So everybody can ask his question. Yes, Hossein, please ask your question.
Thank you very much for this nice presentation.
You are welcome.
I have two questions. The first one is related to the example number 2.
Okay.
I didn't exactly get the reason that you use the swap mesh for the sweep mesh. Yeah, sweep
Yes.
mesh for the larger part of the body, because you change it to the structured mesh pattern, but I didn't exactly why did you change the below part, the larger part to the sweep mesh. This is the first question.
Yes.
And the second one, is there any toolbox in Abaqus for definition of dynamic mesh? I mean, for example, for the additive manufacturing, when the the moving load, when the
no. Or I can say I don't know. I know what you mean. You mean that when the heat source moves, then the mesh changes with it. It is dynamic mesh. It is dynamic mesh. Yes. And actually, first it was implemented in the CFD simulations. For example, when they simulate the trajectory of a bullet in the air, around the bullet they have a small mesh, and in the other regions they have a large mesh. But in Abaqus, I have not seen this at all, and actually I think there is no tool. I think, and but I'm not sure. But I think that there is nothing for dynamic mesh in Abaqus, because or if there is anything, I think it must be coded. Okay, a code must be written for it, for the dynamic mesh, but I don't know whether you must write a script or subroutine. Okay, even I don't know this. I think that there is no tool for it, but I'm not sure. And about your first question, actually, first of all, it was when we defined partitions, then all of it was green. Okay, all of the regions changed to green. Okay, but as I want to define mesh transition zone here, because I want to have efficient simulation, I want to have a smallest number of elements to have an efficient simulation. So I want to decrease the number of elements. Okay, I want to decrease. So because of that, I changed the meshing method to sweep. Okay, for these regions. They are far fields. Okay, they are far fields. I changed the meshing algorithm to advancing front, and also I want to use hex elements. Because of that, I changed the color to yellow and advancing front method. That's it. Because of that. So
okay, thank you. So if you use the structure in
yes.
the below part, so the only difference was related to the size of the mesh around the nozzle.
I will do. I will do. Please look at okay. What I do. Copy. A copy. So everything is copied. And you tell me to change it to green. Okay? Let's see what happens. When we change it to green, okay, Abaqus don't notice to the seed edge, okay? I mean, it doesn't obey my seed edge, okay? It doesn't follow. Sorry, it doesn't follow. It doesn't follow. No, it followed. It followed in this case. But also this one is good. Yes, this one is good. I didn't try this before the webinar, but also this one is good. Yes, it followed. In this case, it followed.
If you delete the seed edge and after that changes to the structure type, maybe it will differ.
Maybe. Let's try. This is also a good pattern. Thank you for your suggestion. Maybe in my next tutorial, I use this one. So I delete these. Oh no, sorry. As you can see here, it is better actually because the element size is changed more gradually. Okay, and here we have a kind of uniform mesh or near uniform. It's also not bad, but I prefer this one. And any other questions you can ask, because Google Meet didn't give me warning or error, so we can continue until morning. And also it is recording. You can ask your questions if you want. I will be glad to answer them. No question? Yes. Please ask. You can use your microphone, Pratik. Yes, you are audible. But please touch. Yes. Please increase your voice.
Okay. Am I audible now?
Yes.
Yeah, thanks for the nice presentation. My question is in the terms of payment. So payment suppose I have 3 layers. I'm designing 3 layers of a payment.
Yes.
And so basically, suppose I am using a moving load and it goes in the center of the lane here.
Okay.
So I define a fine mesh in the center of the lane with suppose
yes.
Of 0.25 meter range that and as the payment stretches, I'll use a chorus mesh here. Okay.
Yes.
But the thing is, I have 3 layers here. So do I need to mesh with the same specification for all 3 layers here? For example, suppose in the middle I have a fine mesh, and apart from the middle, if it's the stretch goes, it has a coarse mesh. For the second layer, do I need to do the same? Because my area of interest is only at the top of the layer and at the bottom of the layer. Like the middle layer is not important for me. So
Ah, okay, this is the pavement. Okay, you have one moving load or two?
I have one moving load here.
One moving load at the center?
Yes.
Okay, this is the moving load. Okay, here this is the line for moving load. What actually what should I do? Here, please turn off your microphone. Thank you. I do the partitioning in this way. Okay, I do the partitioning in this way. And for example, yes, and do the seeding or bias like this. Bias is in this way. But here, uniform. In these lines, uniform. Why? Because this is our stress concentration region. Okay, this is our stress concentration region. And for example, if your pavement is constructed of several layers, for example, like this. For example, like this. Okay, I do the partition again in this way. And I do seed edge like this. Okay, and like this. Yes, also on these ones, uniform. On these ones, uniform. And also these ones. And here also bias, because they are opposite each other. I told you opposite ones, they must have similar settings. Yes, that's it. I think this is good. I think this, but here we don't have any kind of mesh transition. Okay, and here actually all of them are hex, and this mesh can provide accurate result for us, and this is acceptable. Is any other questions? Do you have any other questions? No? So if you don't have any other questions, we can end the webinar. And thank you so much for your participation. And here, when I upload the webinar on my YouTube channel, I will here I will put several videos, several related videos. Yes, yes. Please ask your question. Hi.
First of all, thank you for your time and your presentation.
You are welcome.
I don't have any question. I want to thank you for your time, and I am contacting you on Telegram, but you did not reply. Can you reply? And I want to talk about something.
Okay.
If you have.
Okay. I will. Any other questions?
Thank you.
You are welcome. Any other?
Hello.
Yes.
Thank you so much for this nice tutorial.
Yes, you are welcome.
I have I asked question before on WhatsApp.
Yes, I will answer you because of the webinar. I didn't answer. Yes, I will.
Thank you so much.
And
additionally, is there any exclusive content for Abaqus tutorial?
What do you mean?
Mechanical special content.
Actually, what you purchased, okay. It is the most complete package we have for mechanical engineers, and you have already received 8 chapters, okay. And when you buy the remainings in your next installments, you will learn more. Okay, you will learn more and other aspects of Abaqus. Yes, that's it.
Okay, thanks so much.
You are welcome. Okay, thank you so much for your participation. And I told you that when I upload it here, I will put several other related videos here. And thank you so much for your time. And thanks Google Meet that didn't limit us for 1 hour, and it's very good. But we had this limitation in the previous webinars, and I will hold a webinar every 3 or 4 months in this year. And yes, I think we will have 2 or 3 other free webinars in this year. So finally, have a good time and goodbye.